Hello everyone, welcome to the session. In this session, we'll see work energy method to solve the problems on kinetics. In the previous session, we solved the problems of kinetics by Newton's second law and D'Alembert's principle. Once again, we recap that previous session, how we solved, on what basis we solved the kinetic problems. See here, from the Newton's second law, we have a force equals to mass into acceleration, right? And which is nothing but F equals to ma. And this is the fundamental equation of motion to solve your problems of kinetics from the Newton's second law and the D'Alembert's principle. And moreover, we can also call this as principle of kinetics or law of kinetics, right? But in this session, we will see how to solve your problems through work energy method. Before that, what is work energy method? Work done is equals to change in kinetic energy. And what is this work done? Work done equals to force into distance. And what is change in kinetic energy? Of mv square is the kinetic energy, right? It is your final kinetic energy, and the of mu square is the initial kinetic energy. So final kinetic energy minus initial kinetic energy is your change in kinetic energy. And this equation we call as work energy method. And moreover, we got this from principle of conservation of energy. And from these two equations, you can see one thing. This is belongs to your Newton's second law and the D'Alembert's, and this belongs to your work energy method, right? And if the problems are related with the force and the acceleration, okay, if the problems are related to force and the acceleration, we can solve the problems by fundamental equation of motion or your principle of kinetic energy, which is Newton's second law or D'Alembert's principle. But if the problems are related to force, displacement and the velocity, then you can solve those problems work energy method, or else you can use the principle of conservation of energy. Now we will see the derivative part of this particular equation, which is work energy. See, first we know what is the work done by the force, which is force into distance, right? Which is F into S. Work done is F into S. And next, kinetic energy is of mv square, mass into velocity square. And the next one, work done by the force is equals to force into displacement, right? What is force? Force is ma into displacement S. But from the equation of motion, we have a relation that v square minus u square equals to 2as. Is it right? V square minus u square is equals to 2as. And if you bring this 2as to this side, it will be like divided by 2a, and finally your s is equals to v square minus u square divided by 2a, and you can write here, and the force is ma and the distance is v square minus u square divided by 2a. And if you resolve this, what you're going to get is, you can cancel this a, and finally mv square divided by 2 minus mu square divided by 2. What is this v? Final velocity. U is initial velocity, and this total component will be your final kinetic energy, and this component will be your initial kinetic energy. So the work done is equals to final kinetic energy minus initial kinetic energy. Simply we can say it as change in kinetic energy. So now the work done is, if you take this off as common, then what you're going to get is 1 by 2 into mv square minus mu square. Okay, and finally you can say this as work done is equals to change in kinetic energy. And now we'll see the same change in kinetic energy, that means change in kinetic energy of the bodies for the different motions, like translation, rotation and the general plane motions. We have three different motions. For that three different motions, we'll see how to write this kinetic energy or work energy equation. We can call this as work energy equation. And now the kinetic energy of a body in translation. The first one is for translation, and this is one type of motion, okay, translation. So for this we can write the work done is equals to of mv square minus mu square, and this is what you seen just now. And we'll see the kinetic energy of a body in rotation, and we can write the work energy equation for rotation as work done is equals to of I, which is mass moment of inertia with respect to the center of gravity, into omega 2 square minus omega 1 square, which is like final angular velocity, and this is your initial angular velocity. And if you want to know how you translated the velocities to angular, we have a notations in the previous session of rotation concept. You can go through that. And this is the mass moment of inertia I, and this is angular velocity final, and this is angular velocity initial. And now we'll see the same kinetic energy of a body in general plane motion, which is translation plus rotation, right? And this is the work done, that equals to of mv square, and this is the kinetic energy for translation, and this is the kinetic energy for rotation, right? And this is of mass into velocity square, and this is of into this is the mass moment of inertia with respect to the center of gravity, and this is the angular velocity. Again, once again, this is for kinetic energy for translation, this is the kinetic energy for rotation. And moreover, we can solve the same problems of general plane motion with respect to the instantaneous center, right? So if you want to take that instantaneous center into the account, then your work done is equals to of into your moment of inertia from instantaneous center into angular velocity square. So this is how you're going to write your work energy equations for translation, rotation, and the general plane motion. And now we'll see the work done for some different cases. Okay, the first one, work done in overcoming the force of gravity. When a ball is there or when stone is there which is falling freely, so for that there is a work done, right? So the work done for a free falling body is, which is mgh, that is your potential energy. Okay, and this is also your one type of energy, right? Kinetic energy, potential energy, mechanical energy, electrical energy, all these are energies. So you can replace the kinetic energy with potential energy or any other energy, and that will become as your work done is equals to some energy. So by that only you are going to get the work energy method. And now coming to the second one, body moved horizontally inclined. See here, you have a inclined plane which is of theta, and now here you have a body, and the weight of your body is mg, which is acting downwards, and this is your mg. And now if you resolve that into two components, you are going to get one component here, you are going to get another component here, and the component for this is mg sine theta, right? And now this is this component is mg cos theta. And the work done what you had here is mg sine theta into s. Okay, how you got this mg sine theta? That means work done is force into displacement, right? The equation is force into displacement. What is the force that is acting downwards? See, when it is acting, when the body is moving horizontally inclined, it will slides down with the force of mg sine theta, right? So you took that which is mg sine theta, and the distance is this s, right? The distance which is covered by the body from here to here, and that is the distance s. So in this way you're going to get your work done, which is force into s. The force is mg sine theta, the displacement is s. So now what is this particular length, which is h, height? And now from the sine formula, which is like opposite side by your hypotenuse, h divided by s is equals to sine theta. So now if you bring this s to this side, what you're going to get? H is equals to sine theta into s. So you can write this s into sine theta as h. Again, what you're going to get your final formula, which is mgh, right? So the potential energy is by virtue of its position, right? So when it is body is moving on an inclined plane, it will change its position. Because of that, you're going to get the formula which is mgh, which is equals to the potential energy. And now coming to the next one, body moves against resisting force, which is resisting force is nothing but your frictional force. See, we have a horizontal body, horizontal surface, on that we have a body. And now if the body is moving in this way, your friction is acting in this particular direction opposite to your motion or your applied force, then this particular friction will become as your resisting force, right? Then what's your work done? We require this force, and this force is equals to your resisting force. So the work done is resistance or resisting force, the frictional force, into your displacement, how much you moved the body from one point to another point, right? So you can if you don't know the force, but this force is already equals to your resisting force, right? How much it is going to be resist, that much of force be required to move the body. And if you are moving the body to the some extent, then you have to take that distance. So your force, resisting force or frictional force, into again the distance, is your work done. And this work done for the case when the body moves against a resisting force. And coming to the next one, the body accelerated up an inclined plane by an effort p. Now we have a inclined plane of angle theta, and now your body is here, which is weight mg, that is acting downwards. We already seen the components like mg sine theta here, mg sine theta, and here you are going to get a component which is mg cos theta, right? And you are having some effort which is p. Now what will be your work done? Your work done, see, it is accelerating, that means it is moving, right? So the total resistance plus ma, the force, which is nothing but your effort or force, into displacement or distance. What is your total resistance? And this is your friction mu r, okay? And this is the mg sine theta, the force which is acting by a body, the component of your weight which is acting in this particular direction, which is mg sine theta. And the mu r is the friction. See here, at this particular point we have a friction which is mu r, right? So this is your friction plus, and this is your effort which you are making, and that is your ma, okay, into s is the displacement which you moved. And finally what you're going to get is your total force, okay, the resisting force plus the force which is acting on your body, into the displacement s. This is the work done for your body accelerating upon an inclined plane by an effort p. And the next one, if the spring work done, okay, what is the work done by the spring? That equals to of f into your change in the distance. That distance is nothing but your maybe extension or contraction. Now what is f? And that f equals to k into delta x, which is your change in length. This is k is stiffness, okay? You can see here, this k is stiffness. So now off into k into delta x square, which is your extension or contraction square, and this is your work done for the springs. Now we'll see small problems on this. A block having a mass of 50 kgs has a velocity of 15 meters per second horizontally on a smooth frictionless surface. Okay, frictionless, there is no friction here. And what force to be applied to the block for bringing the block to rest after moving a distance of 37.5 meters? So now the block is 50 kgs and it is moving with a velocity of 15 meters per second, but it brought to the rest after moving the distance of 37.5 meters. So the initial velocity is 15 meters per second and the final velocity is 0. Clear? And the mass of your body is 50 kgs. On a horizontal surface we have a block which is moving with the initial velocity 15 meters per second. but the final velocity is 0 after moving a distance of 37.5 meters. Now what is the mass of your body? 50 kgs. Velocity u, which is 15 meters per second. That is velocity at point A. And what is your work done by a force? This is change in kinetic energy. What is work done? Force into distance. And that equals to, see, first what we require actually, what force to be applied. Okay, what force to be applied on this particular body. And kinetic energy is of mu square of mu a square, and your final velocity is 0, so that's why you're not taking the change, you're taking directly as initial velocity or initial kinetic energy. And now we have a displacement which is 37.5 meters, half is their mass 50 kgs, and next initial velocity is 15 meters per second. So if you substitute and if you bring the value to this side, you're going to get the force as 150 newtons. Okay, you can see here the total quantity of this is 5625 newton meter, and after bringing this value to this side, you're going to get divided by 37.5. If you simplify this, you're going to get 150 newtons. So the force what we required on a block for bringing the block to rest after moving a distance of 37.5 meters is 150 newtons. And the next one, a hammer of mass 400 kg falls through a height of 3 meters on a pile, that means nail, okay, of negligible mass. So this pile does not have any mass. If it drives the pile 1 meter into the ground, 1 meter into the ground, find the average resistance of the ground for penetration. Now first we'll try to understand this problem. See, here we have a hammer which is of mass m, that is 400 kgs, and from a height of 3 meters, okay, it falls on a pile or a nail, we can call pile, and for this nail we have a negligible mass which is 0, and it drives the pile 1 meter, the distance 1 meter. See, this is your ground surface, okay, ground surface. So from here it will penetrate 1 meter into the ground. So what we require is average resistance of the ground for penetration. So this ground will give some resistance to the applied force, right? So we require this particular resistance of this ground for the penetration. Convert this mass into weight, which is into G 9.81. You can convert that in kg into newtons. That means mass into weight. And now the velocity of a hammer impact when it is falling from certain distance, your velocity will be square root of 2gh. And what is your height? 3 meters. And if you substitute that, you are going to get the velocity as 7.672 meters per second. And now what is your kinetic energy of the system? See, this is your mass of your hammer, and this is the mass of your pile, which is 0, and the mass of your hammer is 400. Just now we find that the velocity is 7.672 square, and after substituting all the values, you are going to get 11,771.9 newton meter. From the work energy principle, we have the total resistance into the distance, that equals to kinetic energy. We already got this kinetic energy, right, which is 11,771.9. But what is this? This is your resisting one by the ground, and this is the weight that is acting by the hammer, 3,924. If you add these two, what you're going to get is 15,695.9 newtons, and this is the resistance of your ground to penetrate the nail into it. Now we'll see the next one. An engine and a train having a load of 300 tons are moving on a straight horizontal track with uniform speed of 48 kilometers per hour. If the frictional resistance is 69 newtons per ton, see, you have to underline this, frictional resistance, okay, frictional resistance is 68 newtons per ton, okay, per ton it is making 68 newtons resistance. For 300, how much of resistance it is there? We'll calculate that. Calculate the power exerted by the engine. We have to calculate the power. If the train moves up a gradient of 1 by 1 in 200. Okay, this is the gradient, and that means the slope. What additional power is required to maintain the speed? See, here we have two problems. The first one is when the train is moving on a straight line or straight horizontal track, what is your power? And if the train is moving up gradient of 1 in 200, that means on a slope surface, and what is the additional power we require when it is moving on a horizontal track? When the train is moving on a horizontal track, we have some power which is exerted by your train or engine. And now when the same train is moving on a gradient or inclined plane which is 1 in 200, then what is the power you require? And after that, just relate these two, how much additional power is required than these when the train is moving on a horizontal plane. See here, this is the second case. The first case is the train is moving on a horizontal one, and this is the figure for second case, and this is the figure for first case. And the mass of a engine and train is 300 tons. You can convert that into kgs. 1 ton equals to 1000 kgs. And now convert that mass into weight, which is 9.81. You will get the weight of your train is 2943 into 10 to the power of 3 newtons. And what is the speed? Uniform speed is 48 kilometers per hour. Convert that into meters per second by multiplying with 5 by 18. So you're going to get 13.34 meters per second. And now the frictional resistance is 69 newtons per ton, but we required for 300 newtons. So the total frictional resistance, which is Fr, is equals to 68 into 300 tons. So this is for 300 tons, and that you're going to get 20,400 newtons of frictional resistance. And now first we'll say the first case. The train moves on a straight horizontal track. Then what is the force exerted? And the force exerted on a train is frictional resistance, which you already find it, which is 20,400 newtons. And the power exerted by the engine, P equals to, the power formula is force into velocity, and we have the force which is 20,400, and we have the velocity 13.34, which we find it already. And if you multiply these two, you're going to get 272.13 kilowatts. This is your power generated or power exerted by the engine when it is moving on a straight horizontal track. And now we'll see the power generated or power exerted by the engine when the train is moving on an inclined plane, which is 1 in 200. See, this is your second case. The train moves up a gradient of 1 in 200. What is this 1 in 200? Which is nothing but sine theta, that equals to 1 by 200. And the weight we already find it, 3943 into 10 to the power of 3 newtons. And now we'll find the force exerted, which is equals to frictional resistance plus the component of the weight along a track. That means when the body is on here, so you have a component which is mg sine theta, and mg is nothing but your weight, so you can replace this mg with weight sine theta. So your frictional resistance also acting in this direction, which is mu r, right? So this is the frictional resistance, and this is the weight or component of a weight along a track. And if you substitute those two, you're going to get 35,115 newtons. And what is the power we required for this when the train is moving on a gradient of 1 in 200 is the force which we find just now into velocity, that is 35,115 into velocity is 13.34, and what you're going to get is 468.43 kilowatts. And now what is the additional power we require? See, this is the power when the train is moving on a inclined plane, and this is the power when the train is moving on a horizontal plane. So if you neglect this particular part from the train moving on an inclined plane, you are going to get 195.298 kilowatts, and this is the additional power we required when the train is moving on a inclined pin. Thank you.